So Nick played for Whitney. He plays for the Frosh soft team for Whitney High, and they played Davis High School on Friday, and he had a nice volley goal, and it was perfect because it was his best friend on the team, Eric, right here, crossed it to him, came in and got just enough of it. It's fun stuff. So today we will do the announcements, and then we'll do some of chapter 8. We're not going to get through all of chapter 8, and the material we get through chapter 8, I'm going to try to make it so that you learn it now in the lecture, or if you practice just a little bit after lecture, you should be good. So you can come early to lab today. Oh, that's actually this come work in lab early. That's just applying to Monday, Tuesday, huh? Wednesday, Thursday, we'll have the exam. And then turn in assignments. You could turn in assignments until Saturday this week. I'll accept them. I think Canvas closes after Saturday. So if you want to contact me after Saturday, just use the school email. And so be strategic about your time this week, because we're at the end of the week, end of the semester, I mean. And if you have like a lab report that's worth 20 points that you might lose a few points being late, you should probably decide to make it late instead of working on that and not studying for the exam, which is worth 200 points. It's worth a lot more points. And then the distillation and GCMS, that one's all online, so that's a good example. You might, if you don't want to use up too much time on this assignment until you're done studying for the final exam. And ending out the semester, today we have a kind of normal lecture. We'll go through chapter 8, and I will try to teach it with a lot of examples. And then Wednesday is the last lecture of the year, and that's the final exam review. I'll work through kind of whatever you want, but I imagine I'll do like some cyclohexane chair conformations or pKa questions, things like that. Well, actually, I'll do some of those today. So, and then locker clean out today and tomorrow. So you can work in lab today, but then once you get your lab work done, we'll have you checking out of the lab and you can get extra credit. So if you have all of your equipment in your locker, no extra and not missing any, after you've gone through and requested things you're missing and all that, and everything's nice and clean, so it sparkles, not dirty glassware in there, I'll give you an extra credit point. And if you want, you can clean out after you do your locker another student's locker that dropped out of the course early, hasn't been around for a while. Also, if you want to just clean another area of the lab, you can do that as well. It's a lot of extra credit opportunities there. And let me know on Canvas if you did no November. I've seen a number of those. And then final exam details. I went over this before, but I have a slightly different, so a few more details that I didn't have before. So you could still come in early, and if you can come in early, it's good to have that extra time, unless you're getting some good studying done, keep studying. So you come an hour early before all your lab sections, basically. And then you, as always, put your cell phones up front, no notes. Come in quietly if others are taking the exam, and exit quietly, if others are taking the exam. And then the exam will be cumulative, more cumulative than the other ones. And I'll basically explain that now. So as I said before, this is the same. Know the SN2, SN1, E2, and E1 reactions. You have to know those mechanisms in your head. Like you should be able to see every step of the mechanism in your head without any problem. After you've practiced enough, then it makes everything else clear. If you're kind of like guessing at the mechanism each time, you're not sure, you're not going to do well. And then, so it's just practice. And then I do like the E2 reactions, and I've been helping some of you with this, and almost everyone's not so good at this initially. So get help with this, come to office hour, because this is on the exam. And it's just a skill. You just have to practice it, and you'll get it. And then I like, and I'll definitely ask a question where you don't know whether your major reaction pathway is SN2, SN1, E1, E2, but you should know things that then decide it. So like, oh, it's a tertiary electrophile, it can't be SN2, or it's a methyl electrophile, it can't be E1 or SN1 because you can't make the carbocation. So figure out that stuff. And then the mass spectroscopy stuff, yep, expect that on the exam with the multiple spectrum problem. So instead of giving you the molecular formula, I give you the mass spectrum. And then chapter 8 material. So here's the new stuff since the last lecture. So I'm going to have outcomes 1 through 13 on there. I might not ask you about every outcome, but be prepared for that. And most of these 1 through 13 are pretty straightforward stuff, like some G-Chem stuff. And then I will ask you to name an alcohol. That'll be our nomenclature. You know, I usually start with a nomenclature question. I start with that again, and it'll have a stereocenter. So you have to decide R and S and put it parentheses out front like we've been doing. I'll do some examples in lecture today. And I will ask you to make an alkoxide. An alkoxide is just a deprotonated alcohol. So we'll use a strong base that's going to have a product favored reaction, and I'll ask you to calculate the K equilibrium. So this is newish, but not really. This is just a review of acid base. So review your pKa's. And then I could ask you a question to compare and contrast resonance and induction, and I'll define those today. It's not too hard. And I will ask you to make alcohols. I'm going to ask you to make, I could ask you to make all of these or some of them, like a methyl alcohol, primary alcohol, secondary, tertiary. I'm going to do a bunch of practice on that today, and hopefully it's easy. This is basically like a review of chapter 7, because you have to decide whether it's SN1 to be appropriate or SN2. And older material, I had this before: sigma pi bonding diagrams, cyclohexene chairs, Newman's, Fisher's, absolute configurations, relating stereoisomers, radical halogenations. And I decided I was going to make like a partial chapter 8 homework, but I thought, no, I'll just do a bunch of examples in lecture, and those will be enough. If you practice those, you'll be good. So there won't be another homework you have to turn in. And I will have an extra office hour tomorrow night via Zoom in my office at 5:10, I mean. So basically after that 5 o'clock lab, our lab on Tuesday, the last lab ends at 5:05. So I'll make a Zoom meeting. I already put it in Confer Zoom. There's a Zoom scheduled for then. And if you want to come to the lab, you can come to the lab in person or meet via Zoom if you have questions before the exam. And that's it. Any questions about that intro? Oh, I forgot to ask for a student of the week this week. I guess was Cecily. Cecily was our last student of the week. She's going to remain student of the week for the entire break. She will not forgo her crown. Okay, so we got the outline, and then let's go to chapter 8. So alcohols, that's what chapter 8's about. You can make alcohols. Most often it's made via yeast catalyzed conversions of sugars and grapes to alcohol. So if you get the sugars from grapes, it's wine; from wheat, beer; agave, tequila, and you produce ethanol and CO2. So I'll write that out more like a reaction for us. See what I'm talking about. My iPad going here. So if you have sugar, like glucose, let's see if I can draw glucose correctly. There we go. It's got a bunch of alcohols, and they're all equatorial. So here's sugar, or here's glucose, one of the sugars. And its formula is C6H12O6, I think. Let's see. 1, 2, 3, 4, 5, 6. Yep. And 12 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There we go. And so it's got a nice cyclohexane type chair conformation, but an oxygen in there. All right, so if you treat this with yeast, it'll catalyze the production of ethanol and carbon dioxide. So that's the bubbles in fermented beverages. Okay, and then you could balance it if you want. I just want you to know that that's how alcohol is made. There's not a like a curved narrow mechanism we're going to learn or anything like that. Just know it. All right, and then the IUPAC naming for alcohols. They're interesting. So they're going to be a little bit different than our normal alkanes. For our normal alkanes, we would say things like if we have, say, 2 methyls here and 1 there, how are we going to number this carbon? Or do we want to number it from the left or the right? So would we want to go 1, 2, 3, 4, 5? Or do we want to go 1, 2, 3, 4, 5? Which way is the way we would name this just pure alkane? The red or the green numbers? Well, I'm pulling up the chat here. Josephine, if you have a question about the homework, ask me during the break. And then, yep, we're going red on this one. Okay, so yeah, why do we go red? Lower numbers. Because if we go red, it's 2, 2, 4 trimethyl, right? You can't get that L in there, that's okay. If we go green, it would be 2, 4, 4 trimethyl. That would be higher. Oh, I got the L in that one. So it's red, the lower numbers. So this is 2, 2, 4 dash. That's kind of a funky dash. Trimethyl. And how many carbons across? Pentane. There we go. So with pure alkanes, we want to have lowest numbers. But with alcohols, now we're going to change it up a bit. We need to have numbering from the closest to the alcohol side. Regardless of the other substituents, the alcohol takes priority over lower numbers. So let me make up an example for that. I'll go to the next panel. So let's say I have like this guy. Let's go alcohol here. Well, I'll get some Stereochem too, why not? And then I got 2 methyls here. So if I number this 1, 2, 3, 4, I'll have the alcohol on 2, and then I'll have 3, 4 dimethyl. If I number that way. If I number the other way, 1, 2, 3, 4, it would be 3 for the alcohol, and then what did I say? 3, 4? It's 3, 3 dimethyl, huh? My bad. 3, 3 dimethyl, and the green one would give me 2, 2 dimethyl. So you might think, oh, that green looks better. 2, 2, 3, that adds up to 4, 7 versus the red is the alcohols, OH, and then we got 3, 3, that's 6, 7, 8. Those are higher numbers, but the alcohol trumps it. That's just the way the old chemists got together and they decided lower number on the alcohol is the key. Okay, so we got our numbering. We're going to use the red numbering again. And we have to discuss how we're going to name it now. With alkanes, we just went with an end in like an ane, right? But when you go from an alkane type of number naming, you go to an alcohol. Let's say like pentane goes to all. So you go from the ANE of the alkane will become OL. So this is a 4 carbon alcohol. So it's going to be a butane. So instead of butane, we're going to be butanol. Oh, I'm sorry. Did I do that wrong? I did it wrong. I knew I would do it wrong. It's just the E. Just the E of the alkane, sorry. Okay. So just the E of the alkane becomes an OL. So the E right here, butane becomes butanol for alcohol. All right, good. So let's give this guy the full name. This one is going to be it's got the red numbers, so it's going to be 3,3-dimethyl butanol. Oh, well, there's actually a couple ways to do this. I like to put the number here. This is how I was taught. 2-butanol. That's how I was taught to do it. And then, but now it feels like, I think most people, they change the rules up. I think both are kind of acceptable, but they tend to do it this way. Butane 2-ol is how you see it most often now. It's like the new modern way to name it. I'll allow you to name it either way. I like this one. I don't know, it just seems nice to see butanol versus butane 2-ol. It's kind of weird, but it's up to you. But I did leave one thing off, huh? I haven't completely named this, huh? What did I leave off?
Stereochem.
Stereochem, yeah. So I got to put that out front, huh? And a dash between there. So what does this one look like? R or S? A, B, C, and D is back. This is an easy one. That looks like R. So it's 2R, 3,3-dimethyl 2-butanol, or 2R, 3,3-dimethyl butane 2-ol. We got it. Okay, so as I said, let's do some more examples so we get good at this. Let's go with I'll make a long one. Let's go. We got maybe put like a meth there. Put down here. And then the alcohol will be here. Okay, so, oh, I'm sorry, I didn't switch slides there. All right, so I've got a bigger one here. And on this one, I've got couple stereocenters. Well, here, want me to make it tricky? I'll make this wedged. This is not a stereocenter, but if I wedge it, it makes people confused. I think it is, but it's not. So how should I number it? Should I number it from the left where I get 2-methyl 3-bromo? Or should I number it from the right where I get the 3-alcohol 3-ol? But the bromine and the methyl are super high. I number it from the right because that's where the alcohol gets me. I want the lowest number for the alcohol regardless of the other ones. So this one's got 9 carbons across. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. And I've got some stereocenters. This one here is R. That methyl beats out quickly. And then this one's S. All right, so I'll name this one 3S 7R. And then my groups here, I've got a bromo and a methyl. Who should I name first? Bromo or methyl? The bromo first, because it's alphabetical. So it's 7-bromo, 8-methyl. And you notice I didn't add any RS for that methyl. It's not a stereocenter. And this is a nonane, so it's going to be nonane. Oh wait, I'm going to do it the way I like it. 2-nonanol.
Wouldn't it be 3-nonanol?
Oh, sorry, yeah. Where did I get the 2 from? 3-nonanol, yep. And the other way to name it is 3S 7R, 7-bromo, 8-methyl, no name 3-ol. Either way is fine. Okay, so we're slowly adding in functional groups to our nomenclature. So this semester we've done alkanes, straight up like linear alkanes, and we did cycloalkanes, and then now we did alcohols. Next up, I think, is ethers. We'll do that in 12B. We'll add ethers into that, and then we'll get into like ketones and aldehydes and acids and esters. And you'll see they're pretty much like this. But the thing is, when you have both, say, and if you have more than one functional group, say you have like an amine and an alcohol, then you have to decide how the thing should be named. Should it be named as an alcohol, or should it be named as an amine? You don't have to worry about that. You don't have to worry about deciding which is which this semester. But I just wanted to let you know that's this thing. So should we name this as an alcohol or an amine? If it was named as an amine, you put the pentane 1, 2, 3, 4, 5, and then you just add instead of E, the pentane, the E of pentane goes to amine. So this would be 2-hydroxy 1-pentanamine. That'd be one way to name it. Or if you're going to name it as an alcohol, you go 1-amino 2-pentanol, and it winds up that the alcohol, people have decided we're going to make the alcohols a higher priority than an amine. And then let's look at another one. Now, what should be higher priority, an alcohol or a carboxylic acid? Well, the chemists got together, they debated about it, and they decided, we're going to go with the carboxylic acid is the higher priority. So this is named as a 2-hydroxy butanoic acid, not the carboxy 2-butanol. So where am I getting all this from? Just a list online, or just from textbooks and stuff. The priorities are carboxylic acids are the top priority. So if you have a carboxylic acid with anything else, you're going to name it still as a carboxylic acid. And then esters are next, and then acid chlorides. Some of these, we haven't really gone over these functional groups. Amides, nitriles, aldehydes, ketones, thiols. And so you can see way down towards the bottom here, where's the alcohol? We got ethers. Oh, here's alcohol. Alcohol is higher priority than amine, like we just said. Now this list, it's kind of like ridiculous. It's pretty long, right? I'm not gonna have you memorize it. I will ask you questions where it's obvious which one is the priority. So, and for this exam coming up, for the final exam, I'm gonna ask you to name an alcohol, but I won't have another functional group on there. They won't have like another carboxylic acid. I could add like a bromide or something like I just did an example, and a nitro, but I won't add a nitro. We haven't talked much about this, but I just wanted to let you know there are these nomenclature priorities of groups.
So we don't have to memorize it even for next semester too?
Nah, yeah, I don't have you memorize it. I think it's something that in the normal world, most organic chemists, if they're naming this stuff, they would put it into like Marvin sketch and have them name it. But if also, you can just look this up, this table, right? So it's kind of, seems like something, and it's not even like reactivity. It's just humans made up the order. So it doesn't seem that important to me to memorize. All right. So we got some nomenclature. And then alcohols have hydrogen bonding. That's something that you get pounded on in general chem. So I hope you're good with that. These ones are just quick and easy outcomes, like I was saying. So an example of the first one is, what molecule do you think has a higher boiling point? Ethanol or dimethyl ether. Yeah, higher boiling point, ether. I mean, ethanol. I think ethanol's boiling point's like 80. Boiling point, yeah, 78. And dimethyl ether, I think it's like 30s or something. It's really low. What? Negative 24. It's a gas. I can't write right now. Boiling points. And this is because of hydrogen bonding. That's how we explain it, because the ethanol can hydrogen bond, and then that means that it can stick together better. And you could see, of course, the bond dipoles, right? Going like, oh, wait, wrong way. It's going towards the oxygen, right? And here as well. So it's got a molecular dipole as well. Boop. Looking good, right? And then the bond angle of alcohols and water, you should know that that's like, I don't know, about 105 degrees or so, because it's got tetrahedral electron geometry. But these, so it should be 109-ish, but then these lone pairs, they can spread out more because they don't have other nuclei over here confining them. So they push these together more. But then the ethyl is kind of big too. I wonder what the bond angle is for that. Water, it's like 104, but it's got just two small hydrogens. Let's see. Yeah, just giving the standard 109. I think it's smaller. That's okay. All right, so, and methanol and ethanol and propanol, all 3 carbon alcohols or less are miscible in water. We see that in lab because they have some nonpolar, but then their overall, their hydrogen bonding and their OH makes them polar enough to be miscible in water. So even like isopropanol, it's got its polar area and it's nonpolar, but its polar area wins out. Okay. And then hydrophobic, hydrophilic, I think you know those ones, right? Hydrophobic is water loving. So we definitely say these 3 carbon or less alcohols are water. Oh, I wasn't reading it right. That's water hating or water fearing. So that would be things like octanol. 1, 2, 3, 4, 5, 6, 7, 8. 1 octanol, that's going to be not soluble in water. Whereas hydrophilic is water loving. Ethanol is water loving. It's miscible in water. All right. So some of these are hopefully obvious. Okay, and then let's do these next couple ones. These are good ones. Okay, primary, secondary, tertiary. This should be easy because we've been talking about leaving groups, primary, secondary, tertiary bromides. Same for alcohols. So let me make up an example here and you'll tell me what we got. Say we've got like an OH here. And 1 off of here, say. And then So what do we got here? What kind of alcohol is this one? Would you guess? Primary, secondary, or a methyl? Primary, secondary, or tertiary? This one is secondary. Ugh. Yep, that one's secondary. And we can abbreviate that with the 2 superscript 0. What's this next one? Yep, primary. Primary alcohol, because it only has the carbon with the alcohol only has one other carbon attached to it. So yeah, that's a primary. And then down here, what do we have? This one, of course, is a tertiary. Good. Because that alcohol is on a carbon which has 3 other alcohols or 3 other carbons attached to it. So the carbon with the alcohol is 1, 2, 3 other carbons. There we go. And then the one that I couldn't draw in this example is the methanol, the methyl alcohol. This one's just methane, and change the E to OL. And I don't have to add a number to methanol. There's only 1 carbon that's on, it wouldn't say 1 methanol, just be there. All right, now induction and resonance. This is something we're going to do a lot next semester, so I want to introduce it now. So induction is the flow of electrons through sigma bonds in space. So and it's due to the differences in electronegativity. So if you have a more electronegative atom, we say it inductively pulls electrons towards it from the less electronegative atom. So let me compare and contrast 2 things. I probably should have that on here too, but the resonance. So induction, that's through sigma bonds and space. Whereas resonance is another thing we describe how electrons can flow through resonance. And through resonance, what is it? What do the electrons flow through in resonance? Not sigma bonds in space, but what? Pi bonds. Yep. So let's look at an example of this. Let's go, I'm going to compare the pKa of acetic acid to trifluoroacetic acid. So which of these do you think is the stronger acid, has the lower pKa? Trifluoroacetic acid. Trifluoroacetic acid's pretty common too. It's TFA, people say. Well, the pKa we know of acetic acid. What's its pKa? pKa of acetic acid is 4.74, I think, but we can just say approximately 5. And the pKa, you looked at of trifluoroacetic acid, you looked that up, and it's a nice one, 0. It's the first time we've seen an acid with a pKa of 0, huh? We've seen acids with pKa's of, positive numbers like 9 for an ammonium, and then negative like sulfuric acid we remember as -7. But we haven't seen something right in the middle, huh? 0. So which is the stronger acid? Trifluoroacetic acid or acetic acid? Stronger acid. It's about 10 to the 5 times stronger. So 100,000 times stronger because it's a log scale, the pKa. So. Okay, so why is that? And let's explain it in terms of resonance and induction. This would be a nice review of the acid base. Okay, here it is. So if I draw out my acetic acid, and I'll color code this. What do I have the acetic acid react with? What's our like standard base for what you most often use for comparing acids? Water. That's what our pKa is based off of. Here we are back at pKa questions. We had these in general camera. I mean, in the very start of the semester, right? There we go. So let's look at this. This conjugate base, acetic acid, has resonance, huh? It's stabilized by resonance, the flow of electrons through pi bonds. This lone pair can drop down there and kick the other one up. There we go. We can draw a resonance hybrid. It's the equal sharing of the electrons through the pi bond. It's -1/2, -1/2. Okay, so we got that. So we look at this and we talk about the resonance because if the resonance stabilizes the conjugate base, that makes it a weaker base and its conjugate acid stronger. So the resonance stabilizes, is that how you spell it? So resonance stabilizes the conjugate base and makes it weaker, and the conjugate acid stronger. And the resonance is electron flow through pi bonds. All right, so now let's check out the TFA, the trifluoroacetic acid, and let's look at its mechanism, its reaction.
So when you say flow, is it kind of like how the electrons are shared through the resonance hybrid?
Uh-huh.
Okay.
And remember, whenever you can spread out electrons, you make them more stable. So I'm going to do it without color just to speed it up. Without color for the reactive electrons, but just for the arrows here. A little different style of the mechanism, but I think you're all good with this. There we go. There we go. Okay. So now this conjugate base, it has resonance as well. Right. And so yeah, you can see that. Beep, 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 beep. So they both have resonance to stabilize the negative charge. But this is still going to be a weaker base because the very electronegative fluorines will pull electron density towards them. Through sigma bonds and space. They inductively stabilize. Inductively, I think that's how you spell it. Charge. So this conjugate base has induction stabilizing it and resonance, so it's a weaker base. Stronger acid. pKa is 0, right? So there's electrons, the negative charge here, this negative charge is being drawn through the sigma bonds to each of these fluorines like that, and also through space. So like directly across, there's experiments that show that it actually just happens through space as well. Like, so not just through the sigma bonds. Kind of nice, right? Okay, so let me make sure we're understanding this stuff. Let me give you another example real quick. So let's compare these alcohols. Let's say this guy's alcohol, and then we're gonna go this one. I'm gonna put a couple fluorines here. And then I'll do, oh, forgot some little pairs there. So of these three, which do you think is the strongest acid? And then which one is the weakest acid? With the highest pKa? It's going to be the left one. And we actually know its pKa. Its pKa is about 16. So I expect these ones to be a little lower. I bet this one's like really close to 16 because the fluorines are kind of far away. Unless actually the fluorine, let's see, 1, 2, 3, 4, 5, 6. It might be hydrogen bonding with that, and that changes things up a bit. Yeah. But okay, so let's say 16, and then these will be lower. The closer the fluorines are, the more they can inductively withdraw the You can think of it actually two ways. After this reacts, then you'll have a conjugate base, right, with the O minus. And then the negative charge can be stabilized through sigma bonds and space. That's one way to think about it. So the conjugate base gets stabilization from the fluorines, meaning it will be less reactive, a weaker base, hence stronger conjugate acid. Another way to think of this, you could think of this also just from the acid's point of view. What is the glue that holds this hydrogen and this oxygen together? What's holding these two atoms together? What's here? It's the electrons, huh? So the electrons are like the glue holding this together. If there's more glue, more electrons, it makes this bond stronger and it makes it a weaker acid. So like this right here, the weakest acid has the most electron density between the O and the H. So it's holding the tightest. It's like it's got the thickest rope holding it. Where this one, the weak acid's got a weaker rope because a lot of that electron density is being pulled away even before it reacts by the fluorines. So do you like that? You could think of it both ways. You could think of it from the acid point of view, like the electron withdrawing group is weakening the bond. And then after it becomes a base, it's stabilized. That extra negative charge is stabilized. All right. Okay, so now we know we could talk about reactions in terms of resonance, moving electrons through pi bonding, or induction, moving it through sigma bonds in space. And yeah, good. Now we just have a couple more. This is the end of 12A 2021. And they're both these. This is just a term, amphoteric. Amphoteric just means you can act as both an acid and a base. So an alcohol can be protonated or deprotonated, just like water. Amphoteric or amphoteric, yep. But then the other two, 11 and 13, they're basically reviews. And number 12, that's a good one. This type of question will definitely be on the exam. And so I can do it real quick. So for this one, I'm on panel 8. Let's go. Hold on. iPad's waking up. So on these ones, you have to consider the regiochemistry and then the stereochemistry. So the regiochem is just placing a bromide on one of the alkene carbons and a hydrogen on the other. So I can draw it out like this initially. And then just add, say, the bromide to the left one. Consider that one first. It could be a bromide, iodide, chloride, whatever, or to the right one. And there's a hydrogen here and a hydrogen there, right? There's two. Okay, so one of these is going to be a good one and one's going to be a bad one. The way you figure that out is you look at your leaving group carbon right here, and then you look one carbon away to see how many hydrogens you have. None there. 0 hydrogens to be deprotonated there. I have 3 hydrogens over here, so I will get an alkene product to this side as well. And then I have 2 hydrogens here. There'll be another one, right? So that means I'll get like the E and the Z alkenes from this side. And I don't want to have 2, 3 different alkenes. I just want the one that was asked for. So this is a poor choice. It's going to give you all kinds of alkenes that you then have to separate. If I come over to this other one and I see, oh, I've got the bromide there and 1 carbon away, no hydrogen. So I don't have to worry about a product from that side. There's no 1 carbon away here. And I just have 1 hydrogen here. So that means that this is a good choice. I'm only going to get, I can set this up to just make a single alkene. So now I just have to add the Stereochem. And this is how I do it. I just put I just draw my bromine and my hydrogen antiperiplanar to start. And then add my groups on where they should be. So if I put the ketone wedged out, then the methyls dash back. And now I want in my final product, the ketone to be on the same side as the hydrogen. So that means I'll just have to draw the hydrogen wedged and the phenyl dashed. And this will only produce my desired alkene. What's another answer? Just the enantiomer of that. So let me show you. I'll just draw out my hydrogen and my bromine antiperiplanar. Okay, and then I draw on my wedge and my dash. And if I, instead of having the ketone wedged, I have it dashed, then I just have to have my hydrogen dashed and my phenyl wedged, and that will produce only that desired alkene. And these two answers are just, they're enantiomers. They are different molecules, but they would produce the exact same product. So you could do this reaction with either an enantiomer or a mixture of them. It doesn't matter. I think these ones, initially they're challenging, but after you practice it, you understand the concepts, it's pretty easy. They're actually easier than going the forward direction ones where you have to like, I might make you rotate the bonds. Okay, so back to our final outcomes for this semester. Yeah, we're gonna pause here. I'll even put a little note. Let's see. Spring 2022. Got a lot of twos in there. Make it big. Okay, here we go. Let's paste this in the Jamboard. Okay, let's make some alkoxides. So we've been using alkoxides a lot, but we haven't shown how to make them in a good way. So here's what an alkoxide is. It's some alcohol that's been deprotonated is all. That's an alkoxide. An example, specific examples would be like methoxide or ethoxide. So one way to make them, a common way to make them, there's lots of ways to make them, but we'll just learn one first. Let's make the ethoxide, say. You start with the alcohol and you add a base strong enough to give you the ethoxide in high yield, like a product favored reaction. So a common one is sodium amide. And the sodium amide is a very strong base, so you tend to react it in solvents. You can't use polar protic solvents. You use like non-polar solvents. Non-polar aprotic solvents. Like this in here is THF. This one's actually kind of polar. It's weirdly polar. THF stands for tetrahydrofuran. It's a really common organic solvent. Tetrahydrofuran. We'll see this more often next semester. And the reason why it has that name is this molecule right here. If you have these double bonds in the ring, that molecule is furan. So can you see how furan has the two double bonds? And if you add a hydrogen up to each of the sp2 carbons, if you add like one more hydrogen here, one more, 3, 4, you've added 4 hydrogens, tetrahydrofuran. Okay, so if you do this, it creates your alkoxide for you, sodium ethoxide, and ammonia. And I'm hoping you see how the mechanism works. This is an easy mechanism, right? It's just acid base. And on the exam, the final exam, I'll ask you to do something like this, a mechanism, just acid base mechanism like this, because it leads in perfectly to review the pKa stuff. So is this product favored? Let's see, what's the reactant side acid? Is it the ethanol or is it the amide? This is sodium amide. Sign is off. So is this so what's the reactant side acid? It's the alcohol reactant side acid. And its pKa is about 16, right? Okay, and then the product side acid is this guy, product side acid, right? If this is going to reverse. And what's the pKa of a amine? 35. Yeah, so review your pKas. You'll need to know them for the final. And so is this a product favored reaction? Yes, very product favored because 16 is a much stronger acid than 35. And I'm going to ask you to calculate K equilibrium again too. So it's 10 to the product side acid, 35 minus 16. So that's 10 to the, what is that equal? If it was 15, it'd be 20. So is it 19? Yep. 10 to the 19, very product favored. So this is how you can make alkoxides. There's other ways to make alkoxides. We'll actually go into more of them later, but this is the one you're getting right now. Okay. So the last outcome, here we go. Making alcohols. Before we do this part, I want to show you this material in the, oh, you know what? I don't know if I linked chapter 8. Let me double check this. Let's see the chapter 8 PowerPoint slides. So let's go animations. Yeah, here they are. So you only need to know the beginning of this chapter 8 PowerPoint slides. I think that's why I didn't link it. I'll just show it to you here. So this making of alcohols, it's perfect thing to talk about after chapter 7 when we're comparing SN2, E2, SN1, E1, all that. And so here's a nice little animation to tell you what I'm talking about. So secondary electrophiles. So secondary electrophiles, they're our most promiscuous electrophiles because they can do SN1, SN2, E1, E2. They can do all of it because they can make carbocations. They're not too much steric hindrance. So it's all about the base, no trouble, if you remember that song. So if you're a base like hydroxide, you have a couple choices. You can hit one carbon away and do E2, or you can come straight in and do SN2. Now, is hydroxide a strong base or a weak base? Hydroxide is a strong base. Good. So what is it going to do mostly? E2. So the major product will be the E2 reaction. So if you want to make an alcohol from this bromide, this isn't a good way to do it because you're not going to get much of the SN2 to make the alcohol. You're going to get mostly alkene. All right, so this is, I'm not going to have you do this mechanism this semester, but this will be next semester, but you'll understand what I'm doing here. So if I'm looking at the acetate as a replacement from the alcohol, instead of the hydroxide, I'm using the acetate. What would you guess? Do you think this acetate's a strong base or a weaker base? Yeah, the acetate has resonance to its electrons can flow through pi bonds resonance and stabilize. So on this one, because the base is weaker, you're going to get mostly SN2. But I didn't make an alcohol, but I'll show you how we can turn this ester into an alcohol. So it's all about the base, no trouble. So if you have a strong base, you're going to get mostly E2. If you have a weak base, you can get mostly SN2. And now, but let's pause that thought. So let's just make these alcohols. So these next reactions will be on the exam pretty much. So if you start with methane and we want to make that into the methyl alcohol, methanol, what can we do first? Can we add hydroxide right away? No, can't add the hydroxide right away because you need a leaving group. But do we know how to put a leaving group on the methanol, the methane? So what we're going to do here, the first step of the synthesis is we're going to put a bromide onto this methane. And we're going to be doing this so often, it'll become completely second nature. And it should make sense to you that this methane, all it is an alkane. And the only reactions we've learned for alkanes is to halogenate them and to do combustion, just to burn them up, CO2 and water, but that's not really helpful. So, yep, we're going to start off with bromination, bromine and light to make the bromo methane. And then we make HBr as well, but we'll be able to purify that away. Like if you just added water, this will react with the water to make hydronium bromide, and this could stay in the organic layer, extract it out, right? And then this guy, if I treat it with sodium hydroxide, that's a strong base. Will it want to do SN2 or E2? So E2 involves looking at your carbon with the leaving group and then going one carbon away and deprotonating it. Does bromomethane have one carbon away? No. So bromomethane, all it can do is E2. This is the only thing it can do because it can't make a carbocation that takes out SN1 and E1. And it doesn't have a second carbon. So that took out E1 as well and E2. So, yep, we can add DMSO, a nice polar aprotic solvent. And we got our methanol. We made it. SN2. So what if we want to make a primary alcohol? Say like, oh wait, so methanol, sometimes bad alcohol manufacturers will have methanol in their alcohol and it could cause you to go blind and it could just kill you. So you don't want to buy any too off a brand of alcohols that might have methanol in it. But now the alcohol that people do drink has ethanol in it, and like Grey Goose vodka has 40% ethanol or 80 proof. And that one you can drink if you do it responsibly. Too much will kill you too, but not like too much methanol will kill you right away. And if you accidentally ingest methanol, it's interesting. What you should do is drink alcohol, ethanol, because your body's enzymes that break down the ethanol will help break down the methanol too. All right, so here we go. Oh, so if I want to make a primary alcohol, I got to start with an alkane again. And the first thing I do every time with alkanes is brominate. And so I got my bromoethane. And what kind of an electrophile is this? It is a primary electrophile. So it will react with sodium hydroxide. Now, sodium hydroxide is a strong base, but the primary bromide, it doesn't have too much crowding. Will I get mostly SN2 or mostly E2 where I deprotonate that one? What do you think? The hydroxide is it's a strong base, but it's a small nucleophile. The primary has a pretty big cone of reactivity. You're going to get mostly SN2. So to make a primary alcohol, you can use sodium hydroxide. To make a methyl alcohol, sodium hydroxide. Just a little bit of E2. All right, now secondary alcohols, that's like a rubbing alcohol if you have just the 2-propanol. Brominate first, and where does it want to brominate? The secondary or the primary? Secondary. We're going to get both primary and secondary products, but an overwhelming majority of the secondary. It'll be, what's that, 2 times 80, 160 to 6 ratio. So almost all secondary. All right, yeah, there we go. Can purify those 2 away. And now if I add sodium hydroxide, will I get the alcohol I want? The secondary alcohol, will that be my major product? No, that'll be my minor product. The E2 will be major. The cone of reactivity has gotten too small for secondary, for SN2 to be major. So we don't want to make our secondary alcohol this way. Can you think of another way to make the secondary alcohol? So yeah, this isn't the way we want to do it. Oh, sad face. E2 is major. Yes. So this is rubbing alcohol, what we're trying to make. Cheap. Don't drink this either. That's not too good. That's poisonous as well. So take 2. What if we brominate? And then we treat it with water and we keep the reaction cool. That favors SN1 over E1. So the mechanism, you should see it in your head. Bromide leaves, you get a secondary carbocation, water adds, and then the water has an extra proton that the second water deprotonates. And boom, there we go. Isopropyl alcohol, SN1 major product. So we can make the secondary alcohol via SN1. And we don't use hydroxide, we use the weak base water. Weak base, weak nucleophile, it'll wait for the leaving group to leave. So see how this is just chapter 7 review. And now if you want to make it via SN2, you can, but you don't have to do this for the final exam this semester. This will be like exam 1 and 12B. You can add the acetate, which is a weak base, and so it'll do SN2 mostly. So much weaker base, less E2, SN2 is major. And then we have to do this reaction we're not learning this semester, saponification, but I mean, you can use it this semester if you remember it, but we'll talk more about it next semester. We'll open the mechanism and everything. So you can, what's called hydrolyze this ester right here to make the alcohol. Yeah, saponification. So don't worry about the saponification for this semester, but you can be happy that you finally made your alcohol, your secondary alcohol. You can use the isopropyl alcohol. This is my grand niece, George, 12 weeks old. He's older now. It's such a cute smile. All right, so tertiary alcohol. How can we make a tertiary alcohol? Talk me through it. What should I do first? Yep, as always, brominate first. And will I get mostly that tertiary bromide? Yep, I'll get almost all that because it's going to be 1700 to 9 ratio. So almost all tertiary product. Good. And now a tertiary electrophile. Can I do SN2 on a tertiary electrophile? No SN2. So I'll just have to go SN1. That's okay. So I can use water, keep it cool so I don't get too much E1. And I got my tertiary alcohol. Easy, right? So oxidations, reductions, that's next semester. So that's it. So let me now let me make sure you're good at this because this is on the exam. I already wrote this question. I want you to be good at it. Let me go back to my Jamboard here. So let's start with the methanol. Talk me through it. Which alkane do I start with if I want to make a methyl alcohol? I start with methane. What do I add? It's the first step of all these. Think of it as you got to get like a handle on the molecule, something you can work with. Yep. Bromine, Br2 and light, H nu. Okay, so this is a methyl electrophile. Can it do SN1 or E1? No. No carbocation can be formed. Okay, can it do E2? No. Need a second carbon for E2 and for E1. Same for E1, huh? So what are we gonna do? We're gonna do SN2. So I can use my strong base slash nucleophile, use a polar A protic solvent that'll favor speed up the SN2. And there we go, we got methanol. Easy money. And you should see this mechanism in your head. It should not be a challenge to see that happening, right? The CH. Oh. Hopefully you're all seeing this in your head. You have like, oh, this big cone of reactivity back here. All right, backside attack. All right, what about a primary alcohol? I'll make a, yeah, I think right now we just can only make ethanol. We can't really do, you wouldn't be able to make the alkane yet from say propane. Because when you put the bromine on, it's going to go here to the secondary spot. But for this ethane, we can do it. What are you going to add first? Bromine and light. And you'll get your primary electrophile. And now, can we use the strong base sodium hydroxide with a primary electrophile? It's primary unbranched too. So the cone of reactivity is pretty big. Still got a big cone of reactivity, right? Because it only has little hydrogens here. Okay, so yeah, we can use the sodium hydroxide again. Maybe I'll switch up the solvent. I'll go DMF. Another polar aprotic solvent. Dimethylformamide. Okay, so we got that. And then this will give me my major product. SN2 is major. I will get a little bit of E2. It would be really good for you to do these mechanisms. And they should be simple already, but if they're not, do on your own. Can't say if I spelled that right. Mechanisms. Okay. All right, we did the secondary electrophiles. What are we doing next? Or no, we did primary. So now we got to do secondary, huh? Secondary alcohols. So how do I start? Bromination, as always, that's what we do with alkanes. And it's going to go secondary as the major product. Yep. And then how are we going to get this on there? Get an alcohol on there? Are we going to go SN2? With a strong base, strong nucleophile like hydroxide? No. You're going to go with which one? SN1, right? So what's my nucleophile for SN1? I need a weak base, weak nucleophile. We're going to go water. And should we heat it or cool it? Keep it cool, favor SN1. There we go, secondary alcohol. You get hydronium as well and the bromide. And this will be another good doyo, the mechanism. Do on your own. Okay. If instead we made the mistake of thinking, oh yeah, I'll do, this is your, let me, so SN1 major. We will get actually a little bit of E1 minor here. If I did sodium hydroxide though, I would get E2 major. So that wouldn't be good. Okay, tertiary alcohols, how are we doing those? This one we can make more interesting too. We can go like, say like this. Let's go boop, boop, I like that. That was good. So what do I start off with? What do I do first? Brominate. And where's it gonna go? Major products here. And I know there's lots of products. I'm just concerned with the major product here. And that'll be the overwhelming major product because it's like 1700 times as fast. I will get a racemic mixture of enantiomers here because when that hydrogen is taken off, it becomes trigonal planar and there's no stereochem here or here. So it's gonna equally come from both sides. And then to finish it off, what am I gonna add? Water. Do I want to heat it up or keep it cool? Keep it cool. And again, a racemic mixture because when the carbocation forms, it will, the water can attack from both sides. And there we have it. We made a tertiary alcohol.
So what about the tertiary carbon on the left?
Oh, shoot. You're right. I don't like that. Good question. Thank you. Let me change it. So what I need to do then is say like add one more carbon here, huh? Is this better?
Yeah.
The stereochem made it interesting, so I wanted to keep that stereochem. Yeah, that's better. Yeah, because I've got 2 carbons on this side and 3 on that side. 2 carbons, 3 carbons, 2 carbons, 3 carbons. Yeah, there we go. Thank you for that. Good save. All right. So any questions about that? Okay. What's that?
I was just saying I don't have any questions.
Okay, thanks. Yeah, so now we're off and running. This is no more new material for the exam. And this type of synthesis, we're going to be doing lots and lots of it. Here, I'll give you a little preview to finish off. Let's see, like chapter 8, retrosynthesis helper. This will be for 12B. That one's kind of a short one. Let me do the longer one. So the synthesis stuff, we're going to be doing syntheses backwards and then forwards. So if I start this animation here, animations. See, from the current slide, is that how you do that? I always forget how to do this. Okay, I'm gonna have to present it from the beginning. So here we are, we're gonna be organic chemists. I'm gonna just go through this part. So when we have an alcohol like this secondary alcohol, we're gonna learn how to take it apart, like do it backwards. And then after we've done this retro, there's many ways you can break that apart. So you're working it backwards like that. And so you can see some of this already, huh? The methane is becoming bromomethane, is becoming this thing called a Grignard. And then this guy's got 2 secondary carbons, they'll become brominated, and then they can make the alcohol, to make the ketone, and they all come together. So we'll start doing this stuff. Look at this. So like here, you're seeing the first part of this. This is a new reaction you're about to learn. Make a Grignard, and then here, that all makes sense, right? Brominate, make the secondary alcohol. And then this is a new reaction to learn, to oxidize it to ketone. And then you add this Grignard you made up here, and you get your final product, the tertiary alcohol. And we'll be learning all these different reactions. You're going to become retrosynthesis masters. So like you'll be doing crazy long syntheses like this. I'm going through it fast, so the side effects don't make sense, but look at all this, how much you're gonna learn. Woo, it's coming. Boom. You made this big monster from these simple starting materials.